Hello and welcome. I'm Bill Wake. We're here working on a basic interpreter, basic language, the old one, a version from the 1980s. And we've done a little bit of work to get comments working so far and a very basic print statement. And one of the things you'd like to print is expressions. We just print numbers right now. But we'd like to make expressions with operators. So we're going to focus on that today. And part of my research, I found the the original description of BASIC, I think, from October 64. So it's, what does that make it? Almost 50-something years old anyway. But it has some little nuggets in it, so I'm borrowing one. It may occasionally happen that the first run of a program will be error-free and give the correct answers. Just thought a nice little touch of humor from them. All right, and then today we're focused on the operators, and we started on these single token ones, minus, plus, times, divide, and exponentiate. We haven't dealt with the relational ones yet because they're a little more complicated, and we haven't dealt with the Booleans yet. Okay, we also haven't dealt with variables, all right, or types, or, we'll get there. All right. Let's get over to our environment. Let's see. Yeah, here's that document. It's the first link on the Wikipedia Basic page. Points to the old document here, a manual for BASIC. Okay, well, one of the things I found was kind of their description of the print and how that works a little better than the description I had from OSI. Okay, which is here. Which is nothing to do with Commodore BASIC other than both being basics. I misspoke the other day about it. But we're working from this one anyway. And you can see, that's almost that's almost the exact text that was in the other one. I just noticed that. Tells you how far behind I am. Well, no, that was the text I copied from there. Never mind. I'll get there. Okay, but anyway, we're focused on here today. I'm hoping we can get through most of the operators and maybe start the variables. We also have to deal with the data types. And reading, again, kind of back in this original manual, there really are three types. They pretend like numbers are the only type, which is a floating point number, but there are some places where they convert to shorts and things like, integer shorts and stuff like that. So we'll get there. All right. So we left off yesterday with a failing test. Let's go look at it. We're starting in on our expressions 1 plus 2, and notice we're parsing at the expression level. So it's not really a private method, but it's more lower down, just so we don't have to have all the overhead of the program around it. And what we expect, if you do 1 plus 2, we expect to see op2 of plus number. So 1 plus 2 in a tree form. Okay. And op2 is from parse. Okay. So we have, we have two types in here, parse and expression. Expressions so far, they can be numbers or they can be binary operations. All right. And that's as far as we are. All right. Now, so what happens when we run this? Well, instead of getting 1 plus 2, we just get a number 1 because we don't know anything about operators yet. All right, so let's get over here. Okay, we did a little bit of work yesterday to extract expression, and right now expression goes to factor, and factor is basically a parenthesized expression or a number. Okay, so you can see we got the 1 plus 2 we got down in here, the number. There's nobody trying to get the pluses. Okay, so we have a grammar for that. Do we lay it out yet? No. Oh yeah, expression goes to factor plus or minus factor. So that is where we need to pick up. We have expression going to factor, but we don't have this part yet. Okay, and we'll just start with the plus. Okay, so we try factor. That's the original factor, and right now that's the only expression in this method or function, so it's the return value too. We're going to capture it for now. Let's call it left. Okay, Um, maybe that's not quite correct. Return left. Okay, so small refactoring. All right, so what we're going to try and do is this star basically tells us there's a while loop, and it looks for plus or minus. We'll just start with plus. Okay, and again, the way this works is the current token is in the variable token, and if it equals the operator, let's see, let's find tokens. Okay, we have an operator for each one. So if it's plus or minus, well, we'll just do plus for now, kind of driving off the test. While token equals plus, we're going to do something. Well, what are we going to do? We're going to capture a factor. Okay, now we have the left-hand side and the right-hand side. Okay. We want to do something with them. Well, we need to build up that operator, to get the operator in there. Okay, so we're going to, I guess I'll keep the word left. I don't think that's too confusing. Okay, so we, let's see. First, we need to do a next token to get past the plus. Okay, and well, let's capture the operator first. Let operator equals token. Oops, we'll just say op. Okay, so operator equals token. So we're going to capture the token because we need to know whether to make an addition or a subtraction, and we don't know until we get the other side. So we got the operator, we got the token, and now let's let's make this a var. Ever operated one of these before? Yes, I have. Okay. All right. So we have left. We have the operator. Let's assign left. We'll make a new one. So now we're going to make a parse or an expression. We're going to make an op2. We need a token, which is our plus, and an expression, Okay. So op2, and the token is op, and the existing left and the new right. Okay. And oops, up to. So if we have 1 plus 2, we got the 1, we got the plus, we got the 2. They're both expression trees, okay? And is plus and minus, all these operators really are left associative, and so we want to form the tree early from that. So we're not deferring anything till the far right of the tree. We're immediately saying, okay, the left hand side is 1 plus 2. So if I did 1 plus 2 plus 3, I've already gathered the 1 plus 2 into a node, and that is the correct interpretation of a left associative. Okay. So the semantics there, that all looks good to me. Let's run that test again. Usually I run them before going on camera, so we're going to pay a little bit here. All right. Yeah, that's pretty much it. Let's go on the next one. Let's do a verifying test. A confirming test is the word I usually use. So I just draw a distinction between generative and confirming. Let's see. So what I want to confirm is addition is left associative. So if I do 1 plus 2 plus 3, I should get op plus 1, 2, and then an op around that. Dot plus, and the left-hand side is this. Is that the op2? Okay. Whoops. That closes that op2, and then there's another value that's the number dot integer 3. Apparently I can't count parentheses. Oh no, apparently Swift can't count them. Okay, so 1 plus 2 plus 3 should be calculating 1 plus 2 first and then adding on 3. And I expect this test to pass. I expect all our tests to pass, for that matter. Okay, so I'm happy we've parsed addition. All right. So yesterday, last thing or so, we worked on lexing the operators. So the structure of an interpreter is, at least this one is, there's a lexical analyzer or scanner or lexer, however you like to call it. And we have to use that to convert the string plus into a token plus. Okay. And we did that yesterday. We started in with the test yesterday, and now we've added some code to make the addition parsing work. Okay, so we match the token, match the factor, and so on. And the result of a parse is our tree, and we've returned that expression as a tree. All right, now to complete this piece, we're going to do the interpreter. Okay, and so basically we're going to give the interpreter an expression. All right, and let's borrow this one. It's complicated enough to be interesting. Guess that. Okay, so let's make a test with addition. Okay, so the parse is, we'll assume there's a program. So I got a little overhead to do the line. Sometimes you're just not as helpful as you would like to be. Integer 40. Okay, and what am I missing? Line, integer. I want to do a print, and print takes an array of stuff to print, close the print, close the line, close the program. Okay, let's put these two down here. Okay. What am I missing? Okay. Well, I'm missing this for sure. Okay, so our program is the same as saying line 40, print 1 plus 2 plus 3. All right. And then we'll do the interpreter. So we're going to give the parse to the interpreter, and our output should be 6. All right. We'll just let this catch up, but this should fail. Okay. Basically, yeah, we don't, all we do right now is we just print the new line, and I'm not quite convinced. Actually, I shouldn't say not convinced. I know we've got some work to do on printing that doesn't work quite the way I assumed it did. All right. So we did not get anything. Basically, the print, let's see, print, interpreter. Okay. Do print. It's got an expression. This is values. If it's a number, then we'll get the the number for it. I don't know. That's not quite. Really, this thing, we want to evaluate it, and okay. The rules for single doubles and integers and strings is more complicated than certainly than our code. Okay. But what I'll say here is this evaluation, this thing should really evaluate each expression and then print the resulting numeric value. All right. Now the real rules, I guess I should document them here somewhere. Okay. So this is kind of semantics. It's nothing in the parse that you can see, but it's the way BASIC wants it to work. Okay. So arithmetic operators, plus, minus, times, divide, and exponent. Okay. They convert their arguments to float. I'll say float. This is the Swift. We're using the Swift type float. I don't know what they call it. That probably varies. Okay, it's probably just number in their minds. They don't have a name for it. Okay, but they convert their arguments to float. Logical operators convert their arguments to short, 16-bit, and they do their operation. And then let's see the relationals. Convert numeric values to float, and relationals can work with two floats, well, two numbers, or two strings, but not mixed. Okay. Well, these two, let's see. Strings can only work with relational operators is a true thing too. Okay. So for arithmetic, we're going to do float numerics. For logicals, we'll convert them to short. And it's actually error if out of range. Well, okay, it's still more complicated. It's yeah, I think, yeah, converts to short, error if out of range. That's probably true enough. Okay, I was worried about it can be a double. It can be 3.5, and I don't know if it rounds or not. Let's do this. Does it truncate or round? I'm guessing. No, I don't know. All right. But this is not reflecting. This is not what we're doing here, right? This is we're sort of handling the case of how to evaluate a number, and the I is only ever in play. I mean, it's only right here that it actually exists. Okay, so let's hide our test, and I just do this. There's no add ignore that I know of. Okay, kind of thing. And let's refactor something. So make sure I'm green. Okay. this is blending stuff, and maybe that's the problem. Okay, so if it's a number, let it equal a value. Well, if it's a number, capture the token, and assuming that's an integer, capture the value, and then that's the value to append. Okay, but really, okay, so really this whole thing should be producing something. I mean, we need to evaluate it. It's either going to come back a string or a number. And maybe this shouldn't get this far. I don't know. See, this doesn't really quite conform to our rules. That's why I'm all flustered here. All right. We have an integer, which maybe we need to keep track of integer because it does seem like there is this type stuff going on. It should have been converted to a double if it's going to be evaluated. Maybe we're just not. Maybe number token, maybe that's hiding information we need. Maybe it should be number, should be the value. I mean, the token has something. But how do we know if we're after a float or an int? Right? We don't know until we see the operator. Unless we let the operator deal with it, but it would be nicer to just tell. Okay, so maybe that's what the print should do. It should evaluate it if it's numeric. No, okay, maybe this. I'm disliking result.append more and more too, by the way. Let's extract this. I don't know if it'll extract it. Okay. It's going to be a little weird. It's going to have an in-out or something. Yeah. Okay. Let's undo that. I think I want to make this thing. Okay. Let var string to print okay, let's go the other way. Somewhere down here, I want to do result.append something string to print plus space again, which is not really the right thing. Okay, and then I'm gonna say var string to print equals nothing. Okay. Never mutated. Yeah, right. That's because I want it that way. Okay, so now if instead of appending here, I want to make this be string to print equals this. Okay. So I started off empty, assuming it does the right thing. It comes up with string to print this I and appends it. All right, let's make sure that's still working. So in refactoring terms, what I'm doing is I'm taking something that embedded a value here and I'm kind of pulling it out. It's, I think I'd call it a legitimate refactoring at this point. This empty string, I guess before nothing would happen, now you'd get a string no matter what. There's a little difference, so it's not a true refactoring, but I think it's capturing what we're trying to do better. And something else can deal with it. All right, now I've pulled this out of the way, so I should be able to extract a method without an in-out parameter, which is my real goal. Okay, so this function, which is, I'm going to say evaluate. Okay, I really want, I didn't quite get there, did I? Let's get rid of this parameter and produce a string. And I should have pulled this into it. So I'm guilty here, I guess. Okay, that's better. This is let string to print equal that. Okay. How am I feeling? Feel like I should run it and find out. Nope. Evaluate a value. An expression goes to string. Okay. Evaluate value and get a string to print. That seems much more accurate to me. The printing, the evaluation is a separate, completely separate thing from printing. So let's treat it that way. All right. Now, this is how bad is this? Okay, I'll take this off again. So we got a number. Well, is that bad? Now we're evaluating the expression. Okay, so one case, what happens is we're really down to the point of evaluating this. All right, what's the result if it's a number? Well, it's the number that was in that token. Whoops, it's the number that was in that token. Okay, let's try a switch instead. Switch value case dot number let token. I think I can do it this way. And default, let's return not implemented. Okay. Okay, so in this case, so now I'm actually doing the evaluation. If it's an integer, blah, 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 turn it into a string. Oh, evaluate to a string, how interesting. This is still not quite what we're wanting, but we're going to get it through. Okay. This should be a null refactoring. A little bit odd, but this couldn't happen before, so it's okay. But now I think we might be ready for our interpreter test. Oh no, yeah, we're ready to make it. We're ready to work on it. Okay, because it's still doing nothing. I don't know if it might have printed 1. No, not implemented. Oh yeah, not implemented because it got the other token type. It got the op2. All right. All right. So now our case, we need to handle case op2. We need a token, and we need a left and a right. Okay, so given... Yeah, I'm already screwed up. All right, let's let's comment this out. Let's put this back. Not yet implemented. I'm getting lazy, but that's okay. All right, let's make sure. That's the thing. I see these little problems, and it doesn't take long before they're real problems. Okay. So the problem I have is evaluate. String is not the right answer in most cases, right? Usually numbers, you want to, like, in adding them, you want the left tree to be a number and the right tree to be a number. And I've already converted it to a string. So I think what I need to do is a format. And maybe this is the point where we have to start tracking types or something. I don't know. All right, so we got this number, and it produces this string. All right, let's inject another layer in here. I'm going to call it format. Func format, and it's an expression, and it goes to string. Okay, and right now we can just say return evaluate expression. All right, that should be fine. Value. Well, nobody's calling it. All right, but let's call it down here. Format. Format. Okay, so string is formatting the value. That sounds much more like a print kind of related function, right? All right, now let's change the balance. The format of string, well, this thing should really return a value. And I guess I'm to the point where I need to make a type out of that. Because value could be an int, and it could be a double, and it could be a string. And actually, I think in the print formatting, we're going to find out it could be a funky tab, I guess I'll say. What's the small step? Well, the small step, let's push it to float. Instead of string, let's turn it into a float. How's that going to work? Okay, so apparently not very well. Can I go for string? Okay, this one, let's make it do minus 1.0. And I'm going to say return here. Nobody should be able to get here. Okay, this is exhaustive, so there's no issue there. Okay, so I'm trying to nudge it towards what I want. All right, so a little small step. I don't mind something that, takes me 30 seconds and how does it not? Oh, this is conditional. Okay, we'll do this down here. Eventually we'll get this straight. All right. Is that better? All right, this should be okay. Oh, is it going to be decimal points or something? Print with value. Oh dear. Okay. One of the things that BASIC does is if it's an exact value, it prints it as an integer. Okay, so I guess I would say interpreter is this string, right? That's the format that's making that decision. Okay, so let's find out if there's a string that takes some formatting parameters or something like that. init, init, character. There's a lot of inits. Subject, I don't even know what that is. Text output streamable. Custom string convertible. It's deprecated. Okay, I don't see one. Let's do the other approach, which is Swift format double without decimal. String format. Okay. Cast it to an int. Somebody says, well, this is kind of... All right, so we're fixing up this. The way we are now, we don't have any decimal points, so I'm gonna .0. What did it say? .0f. Okay. So we're saying right now there's no way to create an actual double. So let's just take this easy way out and get it back to where it was. Okay. So what we did was separate evaluation from formatting. Okay. Now I think we're ready to go back again. All right, let's take this off. Let's run this. Oh, run them all. Print with addition. We got empty line? No, we got -1. Okay, because our evaluation, yeah, this is good. If we came in with something besides number, we evaluated it to -1, and that's where that is. Okay. In reality, we're going to have to get more sophisticated, but we're growing this thing. All right, so that's that one. Let's put the other case back in. Okay, now if... Oh, these things are so... Right. All right, we know we're getting a float from the left and the right. So if we call let operand 1 equal evaluate of left, and operand 2 is evaluate of right. Okay. And then if we return, let's see, if token, well, it can only be plus at this point. Let's return operand 1 plus operand 2. All right. And yeah, we're going to let that be for now. We know we have to look at it eventually. Default will never be taken because we've been exhaustive. Okay. So this is like the amazing, I don't know, to me, it's like I've been doing this a while, and this little bit of code right here is just kind of the amazing thing to me of the whole thing. So we evaluate the left tree, evaluate the right tree, and add them up. And that's all plus does. That's the meaning of plus. And it's like we've defined plus in terms of plus. Okay. But the token plus, right? I mean, it started off as a string plus, the character plus, and then became the token plus. The token plus is totally in our domain of our basic program. And we've shifted over to the domain of Swift floats or doubles or whatever. Okay, float, I guess. All right. Now, all that bragging about how wonderful that is. Let's see if it works. Yay. Okay. But I'll stand by it. You know, it's like this notion of evaluate this by evaluating the pieces and adding it up in this domain. And I mean, there's a whole part of math called category theory that's all about, you know, moving values from one domain to the other. And what if you apply a function in the original domain and you make it so that applying it in the original domain and applying it in the new domain are the same thing. And that's what we've done here. Okay, so this piece, we have a ways to go. Like we're only doing floats and, you know, all this stuff, but still, there's just something very lovely about this. All right. So we've dealt with plus. We need to move on. All right. And what I'm thinking of doing is maybe taking bigger steps. So right now we already have all the tokens for these simple single character operations. Okay. And well, we have more tokens to do, but I'd like to get this together. And I don't know, maybe I'll wait on this one, but the evaluate of minus is going to look all the same except for a minus here. And the evaluation of times is the same except for a times. And, you know, to me that already I'm like, oh, I should put a functional thing in there, you know, and we'll do some sort of map or something. But I think we're at a good point there. Okay, so we're also at a good point for a break. So let's check in. Interpreter can do addition. Yay. Let's check that in. And we'll take like a 3-minute break or so. So I will see you in a few minutes, and we'll come back and tackle minus, times, divide, and so on. Hi, welcome back. All right, so we left off. We've just finished plus. Let's get minus going. So we're already doing the lexing. We get the token for minus, and let's go into the parser. All right, so again, this is... All right, I'm going to break down, and tomorrow we're going to do some parameterized tests, I think. It's just too annoying to repeat stuff like this so much. All right, although, you know, the parameterized test would look like 1 plus 2 plus 3, and then this giant, ugly expression. I don't know, is that better or not? All right, let's just do simple subtraction. All right, 1 minus 2. Minus 2. Well, let's go the rest of the way. Minus 3. Let's make sure the whole thing works. Okay. And because I've already got that while loop in there, I'm not worried about this working. Okay. But this should be dot minus. All right. And the test should fail. All right. The parse... We only got the 1 because we don't know to look for the minuses. All right, and that's here while token equals plus or token equals minus. Capture it, do this. All right. It just gets easier, fortunately. Oh, no. Oh, my return value, I should have taken this example. Let's make sure, yeah. Okay. Oh, and I should have converted these to minuses. Yeah. It's like, if you do it enough, you can convince yourself of anything. All right, so we're parsing. All right, so this builds up the expression with the minuses the way we want. And let's go back to this, our grammar. All right, it was factor plus or minus factor. Guess I can make a little more room. Factor plus or minus factor. And there's the plus or minus. And there's the factor. So, factor plus or minus factor, repeating. All right. And this is why people like parser generators, because, this code is really almost a direct translation of this, although I've added in some semantics to capture the parse tree. All right. Tokens plus, token or minus, that's good. Now it's our interpreter. Okay, so where's our interpreter tests? Okay, print with subtraction. And these are minuses. So 1 minus 2 minus 3 should be minus 4. And we haven't printed anything negative before, so let's hope that works. Okay. And this function, this should fail because we assume it's always plus. So we're expecting 6 as our wrong answer. There we go. There it is. All right. It's always good when your expectations are correct. All right. Now this, so here we can say if token equals dot plus, we're going to return this. And otherwise, return operand 1 minus operand 2. Okay. And I believe that should pass. I guess we can run them all. Okay, and green, so let's commit it. Subtraction works. Yay. All right, but like I said, this is ugly, and when we grow this out, right, it's going to be, if token is plus, then do 1 plus 2. If it's minus, do 1 minus 2. If it's divided, do 1 divided by 2. If it's times, do this. If it's exponent, do that. They're all going to look the same. Okay, so let's put a table in. All right. So what we want to do is map the token, plus, minus, times, etc., the operator, to a function. And I know there's kind of an easy way to do this, and I don't remember what it is. Let's see. Well, let's let operators, its type is token maps to, and then this is a 2-argument operator. Go back to our Stack Overflow or whatever. Let's see, Swift, we want the type of the plus operator. Maybe that'll tell us. Now, Swift pass plus as a function. How to pass a function as a parameter. That's kind of what we want. Yeah, maybe, okay, yeah, we can just say that. well, it's really this. Double double goes to double. Okay, so take text out of here. There we go. So it's some sort of function, okay? Consecutive declarations. Maybe I don't need this. Okay. Oh, now I got 4 problems. Oh, I need this, but not that one. Token does not conform to hashable. Okay. Well, oh, interesting. Okay. Let me go back here. At any rate, what I'm trying to do, and I'll get there in a moment, I want to say the plus token dot plus, and let's do it, equals, okay, and now I want to say plus goes to plus, okay, is that legit? Expected expression after unary operator. Oh, I know there's a way to do this. All right. Really don't want that to be a unary. Okay, let's. Okay, let's try Swift pass operator as a function parameter. And I may be mixing up like what Java allows, or operator. Operators and arguments. No. Okay, there may not be a way to do it. I don't know. I feel like there is, though. Well, we can certainly do that. I mean, that closure will work. Operator methods. Sorted by that. That's kind of what I'm trying to do. Let's find sorted by. Let's look for this. See how they're passing the operator there? That's the kind of thing I want to do. All right. Dictionary sorted. Sorted by operator. I really want the declaration. I really want the documentation. That's more like it. Sorted by element throws goes to bool. Well, I'm doing float goes to, or double goes to double. Why did that not work for me? Okay, I got another way around it. I know it can be done, but this function $1, is it 1 plus 2? Expects 2, but 3. Is it 0, 1? 1. All right. So I'm sure there's better notation, and if I had app code, it might tell me what it is. It's very good about that sort of thing, I think, at least in the IntelliJ world. But this is readable enough that I'm happy to live with it. The other thing was token not being hashable. Okay, well, I think we can just do the same kind of deal here, that it'll synthesize one if you just tell it you want it. Because we have a simple enum and it's willing to do that. Okay, I hope. All right. Let's just build and see if that all... We're not using it yet, so no worries. Should just pass, yeah. Okay. But you can see where I'm going now. I'm going to have dot minus goes to $0 minus $1. All right. And maybe this is float. We're keeping our types straight, I hope. Okay. And now, given that I know my token should be there, well, okay, there may be a runtime error we're going to catch, but I'm just going to get the ones working that work. So if you were to say return operators sub token, that gives us a function applied to operand 1 and operand 2. Okay, instead of this. Okay, so I'm going to probably have to do a bang here. All right, and that's the hesitation I had. Yeah, okay. So I'm saying look up whatever the token, find its operator, and then apply it to the two arguments. Okay, and I believe this is just going to pass. Okay. Now, the problem is if we call it with times, well, we don't have times in there yet. All right, but maybe that's not as big a deal. I'm not worried. I mean, our op2s should be well formed with operators we understand, so I'm kind of okay there. All right. Let's check this in. Okay, so we're going to make the interpreter use an array of functions to evaluate expressions. And, you know, like in the old days, this sort of hash table or, you know, a map of some sort for these things that points to a bunch of functions. I mean, that technique has been used for a long time. And, you know, it's definitely making things easier for us. I didn't want to make a big case statement with, you know, 10 or 12 variations there. All right. So I think we took some duplication, you know, this evaluation thing, we pulled it out into this. That's the kind of evolutionary design thing we're after. And what it does is now, instead of all the work to write out another case here and worry about this existing code, I just add something to a table and it's good. Okay. I like it. All right. Let's go back around again. All right. So let's start with Hoodoo. Okay. We have factor plus or minus factor. We've dealt with that. Okay. The next change to the grammar, we're going to introduce a new layer. So it's going to be term, and term is just going to go to factor for the moment. Okay, so I'm just kind of refactoring my grammar, as it were. Okay. And let's make our code reflect that. Parser, here's expression. Instead of, well, let's just add term in here. Func term throws yields an expression. And right now it's just try factor with implicit return. Okay. And up here we can call term instead of factor. Okay. And test should all pass. All right. So what we see going on here, and this is characteristic of doing these operators through the grammar, you end up with a layer per precedence level. So the way we are now, plus and minus has less precedence than times and less than this. Okay. So we're putting in a layer that can handle the times and divide. All right. And then we're going to later we'll add power, and we'll have to add another layer in here. And then the relational operators, I think they may be even lower precedence, so we'll have to rework it a little. But this one, so now with this in our grammar, it's going to look a lot alike. It's going to be, well, I should probably use quotes to be consistent here. Plus or minus. And this one is times or divide. Followed by factor star. Okay. And parser tests. I'm going to jump my steps a little bigger. And okay, I'll just call this subtraction instead of simple. So instead of starting with the one layer and then adding the loop and all that, I'm just going to do the multiplication in one step. All right. So this should be times. And actually, let's just let's do this. Okay. Test, multiply, divide. Okay, so a little bigger step because we know what we're doing, I hope. 1 times 6 divided by 3. Okay, so the inner one is the times. And the outer one is the divide. Okay. 1, 6, 3. And I just wanted to make it come out as an even integer for now. Worry about that rest later. Okay. Multiply. Okay. So you notice we've done this tree, the shape of the tree, multiple times. I don't know. Maybe it's worth a little helper. I don't know. Yeah, maybe. We'll get it working and then do that. All right, this should fail. And it fails because our term doesn't do the analogous thing. And this is the bad part. Well, let's take the whole thing. These methods end up looking very similar. Like their shape is completely the same. Okay, so we're going to do factor. And yet I don't have a good way because they're all calling different things. Okay, so token equals times or divide. I'll make sure this was, yeah. Okay, so if token equals times or divide, we'll get the skip over the token, capture the op and skip the token. We'll call factor down here and we'll build up our tree again. Okay, so should pass. All right. And it doesn't, I mean, it can feel like it's going too fast, but I think, we did this the slow way and step by step and got the pattern in place, and now it's not so hard. These big ugly things, though, I don't know. Print with multiply, divide. Okay, so this was the divide. 41, 6. This is the times. 1 times 6 is 6 divided by 3. Should be 2. Okay. And the function should fail. Right. So we don't have those defined in the table, so we got to define them. And I wish it would just open the one it has. See what happens if I do that. Dot divide slash. Really, that works. You're not complaining. Okay. Value in digital. All right. And this is Swift's closure notation, implicit arguments $0, $1, $2, etc. But we just need the 2. Oops. Plus, minus, times, divide. Okay. And our interpreter tests. Well, we expect it to pass, so let's run it all. Yeah, that's pretty quick. All right, commit. Add times and divide. All right, let's get back to these tests. Parser tests. I'm wanting some helper functions. I think that's a good thing. All right, the helper functions I want. Let's do one that builds this tree. So, func exper, and we're going to take. I'm going to write it the way you write it. So, integer. I don't know if I'm messing myself up with that. Int 1 of int. The operator is plus. And op is so common when you're writing compilers. Let's just go with it. All right. Op is of type token. And the second integer is an int, of course. And what does it yield? Well, it yields an expression. All right, and the expression is this. Okay, op2, the op is here. This is int 1, int 2. Okay. And let's write this as exper 1 plus 2. Okay, I'm liking it. Build failed? Or you just token has no member op. Okay. And I talked yesterday about like what's top down, you sort of write some lemmas. I'm going to do that here. I'm going to give you this little helper method up top. And it takes some reading to understand it, for sure. Let's format it a little. Op2 int2 goes to expression. Okay. Int1 op int2 goes to expression, which is the tree form. All right. Okay, and now let's see who can use this. Yeah, it's getting down a ways, isn't it? Okay, there's the one we did. Now this we can decide, but op2 plus etc. is really x per what are the two values? 1, 2, 1 plus 2. That takes care of this much. And this is really x per this x per plus 3. And we'll do some formatting to make it okay. So it's the x per consisting x per 1 plus 2. Okay. Wait. Can I convert? Oh. Okay, let's make another helper. I was originally going to have 2 helpers, and now I know I'm going to have 2 helpers. Thought I could get by without it. All right. This one's longer. This is our more our associative expression. And you tell me if ints are right, but op2, op1, and now this is op2, and the expression is this thing. Op2 token takes the operator, so this, sorry, my op2's, let's call this operator. It's blending with my .op2's here. So op2 takes operator 2 applied to op2 of operator 1, number, whatever, int 1 at 2. That's the second expression. And then this one is number, integer, int 3.
I'm right here, honey.
2, there. Yeah. Okay. Well, let's make sure this one's going to work. probably down where this error is, right? Okay, so this should be expr expr 1 plus 2 plus 3. Expr. Okay. Let's make sure these pass. And what I like about this is it's just kind of linear. 1 plus 2 plus 3. Okay. And then this one is 1 minus 2 minus 3. Okay. And this one is expr 1 times 6 divided by 3. Okay. Okay, well, let's check that in. So we created a helper method for small parse trees. Okay. And where does this want to live? I think, does it want to live on expression? I'm worried about these ints as well. Okay. Let's leave it here for the moment. Well, I don't know. See, when I get to my interpreter tests, right, they're full of parse trees. What would it take to put them on parse? And why did I have that problem? Because, wait a minute, I'm a little confused. Normal state. Okay, the problem was they take ints, and I wanted to pass an expression. Okay, and I don't remember how to do these either. My goodness. Let's do an extension. Expression. Is it static? Let's try that. All right. So declaration-wise, that's okay. All right. Let's try and reference that. Well, let's get rid of 1 and let the compiler tell us. Missing arguments. Yep. Okay, so expression dot. Okay. Really, that's the only place we ended up using it. I thought there were more. I guess we put our loop in just by default on the plus the times one. Okay, and same thing here. Make sure that's okay. What I don't know how to convey is, like, these are just little helpers, and I don't know, right now they're mostly for tests. I mean, honestly, they're probably just going to be for tests. Operator 1. All right, and then I want to rename this. I'm going to say make. And same thing here. Okay. So little buildery. Oh, what's your problem? Okay, you got there. Little builder functions that let me build up expressions. The integer stuff worries me, but we'll come back to it and straighten out types a little more at some point later. All right, this should all work. Okay, so we added a builder, well, make function to expression for simple expressions. And it's weird for me to put in helper functions that are really for the benefit of tests and not used by the production code. It may be that we can use it somewhere. I don't know. All right. So then interpreter test was the other place that could use it. Okay, that's all fine. Here's one. This is expression dot make, and our numbers, it's a plus plus 1 2 3 1 dot plus dot 2 dot plus dot 3, and we'll take these out. Okay, I'm liking that a lot better. I mean, maybe this expression extension should live in tests. Let's do that in a moment too. Okay. This is very similar. It's expression dot make 1 2 3 with all minuses. 1 dot minus dot 2 dot minus 3. There it goes. One 6 3 1 times 6 divided by 3. Okay. All should pass. Okay. Use expression dot make in interpreter tests. Now I think if it's on one line like this, all right. I think that's pretty good. I mean, it's yeah. I think this is a definite improvement. You can kind of tell what's going on. um, so I think we're good there. The You might think, oh, here we are spending half an hour on improving these tests, and is it worth it? And I think it really is. That test is much easier to understand what's going on. You you can almost just read it 1 times 6 divided by 3. Admittedly, you could do this at the string level, but kind of doing this at the parse level. Those are Yeah. I could almost see this one, right? This line is your input, 6 space new line is your output. That could be in a parameterized test, no problem. All right, now let's pull this out. All right, another option you have, and I'm going to take it, is to make an extension in a separate file. So this is going to be expression plus make, and notice it's living in the test package. And I put this back in. Okay. I need an import somewhere. Okay. Oh, maybe I can just import BASI. Is that gonna work? Yeah. Nope. And well, let's try testable. Okay, so again, I've put this in the test package, so only the tests have access to this make function, and that makes me feel better because I wasn't comfortable with these ints, because really that's not the semantics that's there. It's just kind of convenient for the test to work that way, I guess you'd say. That is good. All right, so let's see. We extracted expression plus make dot swift for test use. Right. So, and yeah, I'm leaving my code here just focused on the production side. Alrighty. Why did you not pick up? Did I miss one? Expression. I don't know why it didn't want to take everything. Okay. Right. Okay. Now, where are we next? All right. Well, we're improving our tests, which is good. Let's tackle the next one, is power. Now, in a lot of languages, power, A to the B to the C, is right associative, and so you'd have to make sure the tree builds a different way, always assembles the right two instead of the left two or whatever. But at least according to this, wherever it got off to, did I keep that original basic document? Wherever that got off to. According to them, these guys, the precedent, it's left associative, long story short, which means we can take the same pattern. So I can define power is factor, and then to the factor star. Okay, and now I'm going to do this again. I'm going to make this one call the intermediate layer. I'm going to make my code reflect it. Okay, so term calls factor. Let's get power in there. Func power throws yields an expression, and it's just going to call factor. Try factor. Okay, and this can call power. Okay, and that should all pass because we don't actually do anything here. All right. Introduce power to parser. All right. Well, parser tests, again, we've already got the value there. And test power is left associative. Let's make that explicit. Throws. Okay. Let program equal 2 to the 3 to the 4. We'll take all this. Program power Lexer. Now this is 2, 3, and 4, and these are power. And should fail. Token has no member power. Oh, exponent. All right, and again, I think we'll get a 2. Yep. All righty. And again, duplicate. Ugh. And instead of power, we want to call factor. Factor. And token equals exponent. There's no or. All right. If left, try factor. And again, we got the same pattern of building up the tree left to right. And it should just work. Now, interpreter. Well, let's do it in a different way. Let's do a BASI test. Okay. So this one explicitly powers 42. Let's print 2 to the 3 to the 4. We haven't tried making sure our expressions work at this level yet. So and this is kind of convenient, right? We don't have to mess with the trees. All right, so 2 to the 3 to the 4. Let's make it 2 to the 3 to the 2. Lazy. Okay, 2 to the 3 is 8. Squared is 64. Okay, 3 to the 2 is 9. 2 to the 9th is 512. So 64 is the right answer. And if it does right associative, it'll break. Okay, and I hope this passes. Oh no, it won't. We don't have the operator yet. Okay. Where's interpreter? Exponent. And I don't know what Swift does. Is there a math.exp or something? Oh, we got an exponentiation operator? Oh, POW. Okay. Number to a power. Okay, in our case, it's only the evaluation is doing the left associativity. The fact that the operator is not going to be is not a problem. All right, testing. Stop that, and should pass. All right. This is good. So where are we on things? Expressions with single character operators. We've done most of them. Oh, well, most of them with floating point numbers. We really have to get the types straightened out. Straighten out the types. The only single character operator we don't do is equals. We handle parentheses early. Now equals. Let's find that reference. I think it has things to say about things. Okay. Unfortunately, it's not indexed. All right, but we got expressions, names, and variables in 8. Do we have relationals? Yeah, let's start there. Okay. 9 digits with or without a decimal point, possibly with a minus sign. We haven't dealt with the minus sign. Let's make sure we add that. To do, let's say, well, unary minus. Okay, well, we got the factor of 10 thing going. E notation. Okay, variables we haven't dealt with. Expressions. Okay. Yeah, here's the priority. Parentheses first, powers before multiply and divide, before addition. Left to right. They left it ambiguous about the powers. But here, raising to a power a to the b to the c means a to the b to the c. So that's left associative. Not a to the b to the c, right associative. Okay. So why he didn't say that here, I don't know. But, you know, this is a 50-something year old document. So we'll make allowances. And the other one I find funny, well, we'll get there. Less than and greater than aren't in his keyboard. So he has to hand put in the arrows and the less thans. Okay, but we got abs, log. We don't have any of these logical stuff yet. Okay. If x less than or equal 100, statement 10, statement 20, I want statement 40. Exit after. Okay, it's not. I mean, programming language semantics was not even a thing yet. I mean, in terms of like having a firm mathematical foundation or anything like that. So it's all kind of sloppy in those days, and sometimes it's sloppy still. The languages have gotten so big, it's hard to know. I mean, it's funny, they're telling you how do you type a less than and so on like that, you know. So, and a control key. These are things we don't care about. However, we don't have a REPL, and maybe that's something we should get going, because I could see tests that take a file as input that gets fed to the REPL, and we just capture the output there. Okay, let's save. Yeah, this would be stuff in the REPL. Errors. Yeah, here's our quote. It may occasionally happen that the first run of a new problem will be error-free and give a correct answer, but it is much more common that errors will be present and have to be corrected. Like, okay, yeah. And here we are, debugging quotes. We don't use quotes on that anymore. All right, I'm still looking for the statement definitions. Summary is let read data, format, print. Here you can see the comma being used. Elsewhere you can see elsewhere you can see that you don't even have to have commas. You can just put the names right after the strings and stuff. Okay. Any of the 6 relations. Now, it's interesting to me. They define the line number if expression relation expression. That sort of implies you can't say A less than B and B less than C. But we know you can, so, or I'm pretty sure you can. I don't know if I have an example. Okay, no, that's not the end. Okay, here's the stuff about print. Let's see if I can find that example. Okay, yeah, first number equals A, and then number down here, first number equals, well, it turns out it allows for blanks in the numbers. Here you can see there's none. I'm not sure. Here you can see the comma. The comma does a tab to column 15. This one, second number equals B. There's no space after the thing. So we've been adding some spaces in. That's clearly not right. Okay. But I'm after this relational stuff. Yeah, I mean, there's a lot on printing. You can have tables. We haven't dealt with that at all. Subscript 0 to 10. Oh, I really thought it did subscript 1. Huh. Okay. I know it's kind of boring to watch me scroll. All right. Well, this one's another kind of funny line. Ideas for more advanced programmers. And basically put a description. This is called documentation, okay? Like beginner programmers wouldn't need that, but advanced programmers might. Okay. Now, I probably should take notes, but I definitely... Oh, interesting. Yeah, they don't... they had a version because the keyboards didn't have less than greater than, right? You could say LSS and GRT and whatever. That was some special card version. And that description was funny too. Let's see, where did this go? Yeah, a card-operated online version of BASIC is available. Well, we don't commonly speak of batch card systems as being online. um, you prepare a deck of cards, you punch the cards, and so on. It's like, okay. This is why there's a data statement that lets you put in values you're inputting. Okay, I thought there was a description. Oh, here's limitations. This was funny to me too. The length of the program. Well, it's difficult to relate to the basic program, but in general, about 2 feet of teletype paper. Okay, which is, probably 3 screens modern. Okay, we got an if, then relation. I'm going to assume we can have ands and ors with them. Let's see. All right, I think we're due for another break. We've gone an hour. So let's take a break. We will add the equals. I'm pretty sure these basics for if they did a test of 0 or not 0. And so equals will just return 1 for true and 0 for false. And we'll add that last operator. That one can be a little more interesting in terms of interpreter. But let's do that. I'm trying to figure out the balance on these things. Straighten out the types. That's kind of a sticky point for it right now to me. That we're mixing up all these floats and doubles, and we haven't talked about strings yet at all. Okay, track line number. That's another interesting one. We haven't dealt with errors a lot. And I put REPL here somewhere. I'm going to move that up. That might be like here. Okay, so another 3-minute break, and we'll come back and finish equals and maybe start on the types, maybe not finish them. We'll see. Hi, welcome back. All right, let's see. What we decided was we would do the equals operator. So it's kind of our first Boolean, but the result is still a double, so that's okay. Lexer, we parsed it or lexed it, scanned it, and we don't have a test for it yet. Now, okay, the grammar's going to need some revision here. All right, so, and again, we got to worry about the precedence of things. If you say if a plus b is less than 3, you really want to evaluate, well, actually, if a is less than b plus 3, let's say it that way, you want to evaluate b plus 3 as one expression and less than as lower priority. So we have to modify this once again. Let's put another layer in the middle called relational. Okay, and relational goes to this. Well, no, how am I going to do that? Sorry, let's get this straight. Expression. Well, is that term? I don't know if there's a better. Well, whatever we call it. I'll call it value. Okay, we're going to say expression goes to value, relop, value, optional. Okay, so we get a value, or we can do value, relop, value. And we have a question mark because we only allow it once. You can't say A less than B less than C. Okay, but you can parenthesize. All right, I think that's okay. So expression, where's parser? I don't know, value. term. What's the sub-expression? Value just sounds wrong to me. It's too generic or something. Well, let's do sub-exper. Which is not very great either, I'll grant you. Okay. Maybe it's numeric expression. Roll up. We'll leave it for now. Okay. All right. This means we extract out sub-expression. Expression goes to sub-expression. This should be try sub-expression. This throws. Okay, so expression goes to sub-expression. Sub-expression is our old full expression. Okay, it should pass. All right. Good. Okay. And we want to do a test very much like, well, it's really like that first addition test. This one. Okay. Test equality comparison. 1 equals 2. Back when we only used 1 equals mark. Okay. And the result should be 1 equals 2. Okay. And we'll just run them all. All right. And as usual, just the 1. Yep. Okay. Parser. Well, let's do this. Far left equals try sub-expression. Now, this time it's not a while, it's just an if. So, if token equals, then we're going to do something. And in the end, we'll return left. Okay. And it's kind of the same. I hate it. The duplication's kind of boring, but all right. We take the sub-expression. If it's equals, we save that. We try the other sub-expression. And then we return op left, right. Okay, so we return the equals left and right. And if it's not equals, if it's just 42, we got sub-expression. We didn't try and go down here. We just returned the 42. All right, and I think everything should pass. Right, okay. Parse equal relational expression. Okay. I mean, yeah, can we... I guess we would have to... What would make this the same? Well, one thing is the name of the method to call. The name of the method to call gets used twice. The matching the token is there. And maybe that could be a set of tokens, and then it's just token in. It's a while versus a if. I don't know. Like, could I write a generic method that would do this? Maybe so. Yeah, maybe so. We'll see. I'll save it for another time. All right. We parsed it. Now we need to interpret it. And again, I don't know. It's kind of easy to do it up here. Okay. Well, we don't have an if that can look at it. So, okay, that makes it easy. We'll go back over here. We'll do an interpreter test. All right. So if you evaluate print with equality comparison. Okay, program is make 1 equals 2. Well, let's do 1 equals 1. Let's do 10 equals 10. Okay. If that should be a 1. Okay, 1 for true and 0 for false. All right, and this test should fail. Our usual blow up. Okay, and interpreter. This is equals. Oops. Equals maps to. Well, it's really okay if it's 0 equals 1, then 1.0 else 0.0. I guess that's F. I think I can say F. I don't think that's going to help. Maybe I don't need it. Will it cast it to float for me? Okay. And then these parens are probably not needed, I think. Actually, let's keep them. I think it helps communicate a little bit. Okay, we really are doing this comparison. 0 equals 1. So if the two values are equal, it's 1.0, else it's 0.0. And this may be 1. I don't know. I thought I saw it somewhere in here. Maybe it was in that Commodore Basic Guide. But I thought somewhere in here the comparison said it something about converting it to a 16-bit value. But maybe not. Maybe that, yeah, I don't know. I'm not going to read through that again. That's too much. Okay, let's run tests. All right. Interpreter handles equal comparison. I'm going to take... Okay, I think we've done what we said we would do here. Let's take that. So this is 2204. May 12th. All right, so we did most of our arithmetic-y kind of stuff here. Straighten out the types, deal with the REPL, then go back and do more stuff. Well, expressions with floating points is really types as well. Print with expressions, we basically did that yesterday. Okay. Multi-character operators, that's our comparisons and or not. Print with strings. Nope, 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 nope. All right. Straighten out the types. Alrighty. So what's going on here? Let's look here. This number with token. The way token is right now, we only do integers. We don't do floats. We don't do strings. Let's see. Now, I may be mixing up all my basics. It definitely happens. Okay, let's see if we can find the operators in here. I think maybe this is the one I was reading that explained those in terms of... Yeah, here we go. Okay, B less A. Oh, yeah. Okay, here they got B greater than A and A greater than C. All right, so that tells us that AND is even lower precedence than the relationals, and it also tells us we can have multiple ones in a thing. So good. Yeah. Well, this is a little... Yeah, this is kind of what's funny. So and or not can be used in bit manipulation mode for performing Boolean operations of 16-bit 2's complements, which are shorts, basically. And the question is, does equals less than or equal? I guess and or not have to worry about that. So I think maybe what's going on, I feel like, well, if you use and or not, it's going to convert this from a double to a short and use the 16-bit mode. It doesn't treat them as doubles. They don't mean anything as doubles. But if you say if A, B greater than A and A greater than C, is that result of the relational, is that a short? That may be what's going on here. And then it doesn't need to be converted. So there's definitely some subtlety in this. All right. Not Lexer, token. Okay. And then the parse doesn't want to care. I think this is the wrong type. Okay, I think number, maybe, is it number? Maybe it's like value. And then the operators can worry about how do I convert the value. See, I'd like this to be just so boring. I would like it to be unthinking and mindless. That all the conversions are pushed into the tree and we don't have to worry about it, which means the parser is going to have to deal with it. This needs to say, like, if I were to take an integer and do addition, I should convert it to a floating point, to a float. Okay, for this particular these operations, they need floats. But maybe everybody's just a float all the time. That's the tricky one. The exception, at least one exception, is our lines. So a line starts with an integer. The line number is always an integer. You can't say line 42.0. You can say 42. So maybe this integer, yeah, that context needs to know it's an integer. Okay. Let's work on the other side. Maybe we should do a print 42.1 kind of thing, or 0.25, something that comes out even for now. If you said print 42.5, well, this doesn't quite work because it says number, but it's an integer, and then it turns in. But there's nothing that says a number that's not an integer to start with that already is a float. Now, for an expression, an integer should be turned into a float. All right, let's go back to our parser. Down in factor land, maybe that's where it should be converted. Okay, yeah, we kind of assumed if it's not parenthesized, it's supposed to be an expression, which is a number based on whatever the token is. That's not really accurate. It really should be, there really are three cases. It could be a left paren. Let me go to the grammar. Like, what can be in a factor? Well, integer or left paren or a double. Okay, those are all valid. But if it was a times, if we said 3 times times, okay, well, the first times is fine. It's looking for multiply. The second times it comes into factor and says, it's not in a left parenthesis. It must be a number, and it puts the token in. And then interpreter time, like, we don't even catch the error here. But if this is not an integer, then, like, what is it? It's the times. That doesn't make any sense. All right, so I think what this implies to me is the tree for an integer should really convert that value to a double and put it in a double or a float. Okay. Maybe this integer, we have to syntactically handle integer because line numbers are pure integers. But if we're ever using it in arithmetic, it should be a float. Okay, so let's make that happen. All right, now our lexer does not do this. All right, so print, where's a number? Line number. Okay, well, integer 12. Okay, this is about the spaces thing, but you try and parse this, it comes up with 12. Let's find our lexer. Okay. So the rule we have now is you got these digits, and while you've got 0 through 9, it accumulates those digits into a value, into a string, and then builds an integer from it. Okay. What we want to say is we want to grow our rules again. Okay. So factor is integer, or factor is float with a value. Okay. Now the semantics, I think a factor should only be, let's call it number. I don't know, it's kind of a more general number. All right, but the rule for number is number should be, let's write a regular expression. I'll say goes to, but it's 0 through 9 plus, you got to have that. Then you can have an optional dot, and then more digits. You got to have at least one, I think, in basic. Okay. And then you may have an exponent, which is E or E, followed by good old 0 to 9 plus, and this is optional. Okay. So 123, that's an integer. 123.4.5 is fine. 123E2 is fine. 123E4 14 is fine, but 123.34, well, this is not legal. Not legal. This is legal. Okay, 123 dot, 123 dot E3, 123 E, 123 dot 4 E. And actually, I think they allow plus minus optionally. Okay, E minus 14. Okay. Yeah. And then you can have a unary minus on the front too. Okay, so those are some illegal ones. I think we discussed this plenty. Let's take this out. Okay. I don't know where I got this. Logic operators convert to short area of out of range. Somebody said that. Does it truncate around? Yeah, I don't know where I got that. I've got 3 versions of BASIC kicking around I've been looking at. Okay. At any rate, we would like to have a token type that is number that holds a float. Okay. This is only peeling off the front of a float and creating an integer constant, but we can make more tests. Okay. What is check token? Let's make sure that's... Check token takes a string and it gets back a token and make sure it's the expected token. Okay, we can do that. All right, so let's do a simple one first. Test number lexing. Check token. 14 should be dot integer 14. Okay, and that should pass. That's what we were already doing here. Did that run? 11:06. No. I guess I missed. All right. But now let's do some of our floating point stuff. Check token 14.5 should be a number 14.5, right? Which should not even be happy. Yeah. We don't have a number type on our token yet. All right, so let's add it. Case number of float. And we should fail, but at least it should know what it's doing. Okay, integer 14. Yeah, it doesn't know to read the plus. All right, let's add that. Okay, so we got value sitting there. Let's call this the, what would you call it? Well, value will do for the moment. Okay, if the character is there a current program sum index? Okay, I guess we'll do that. If it equals dot, then we're going to go into some floating point stuff. Okay. Let's let I don't know, I'm not what do you call the numbers? Well, let's call it the fraction. Equals match while 0, 9. And once again, I've forgotten to skip my character. Just index plus equals 1. Okay, so if it's a dot, we skip the dot, we accumulate a fraction, and let's make this var value. And let's start off with var is float equals false. And here we definitely know it's a float. Okay. Yeah. All right. Let's say value plus equals dot and value plus equals fraction. Okay, so we're accumulating the full string form. Okay, now again to our grammar. I can say 1, 2, 3, 3, E2. That's not a line number, so we'll not call it an integer. Okay, so that takes care of this stuff. Okay, and there's an error that could happen, right? Because we could have no digits. All right, now if I guess our case didn't cover this, did it? All right, yeah. So when we return, if it's a float, else return that. Token dot number with float of value, and we'll assume the conversion works. Maybe a bad assumption, but let's start there. Okay, so we gather the initial digits. If it's a dot, if we see a dot next, we know we have a float. Skip over that and accumulate the fraction part and save all that in the string. And at the end, we convert the string either to a float or an int. All right. And this, I think, should pass. Notice 14.5 is a power of 2 in the fraction, so it's safe for comparison. All right. Okay, so what we did is we make Lexer no floating points contain dot. All right, now let's check a little more sophisticated. Check token 14.5 E1. So that's 14.5 times 10 to the first. And that should equal number 145. Okay. Actually, let's add both upper and lower in at the same time. E minus 1. Let's convert 1.17.5 should be 1.75. Ooh. Let's not do minus just yet. Fickle. Okay. Yeah, that should fail, both those, because we don't look for E's. Okay. If program subindex equals E, or program subindex equals E, then is float is true, index plus equal 1. We'll skip that thing. All right. And then let exponent equal match while 0, 9, and value plus equals E, and value plus equals exponent. Okay, because the format's the same in the two languages, that's okay. If it equals E or E, it is a float. Skip the E, read the digits, append them in. Okay, and that should pass now. All right, we'll stop there. Add floating point numbers with exponents. And I'll say no error handling yet. Okay, so in our to-do, what we're really doing at this point is we're doing expressions with floating point and handle errors. All right, and the errors are, oh, this exponent is no digits, and or the fraction is no digits. Okay, because I don't think you can say 3 point. Okay, I think you got to say 3.0. If that's not the case, we'll fix it, but that's okay. All right, so we will pick up there tomorrow and get these errors handled in the floating point one just to make sure that part of the program's okay. And then once we have that, we'll work on the types and make sure that basically the operators, we want to deal with it. What happens if there's an integer operand is more or less the issue. And at some point we'll have to add string operands, but that's okay. All right. Well, thanks for joining me today. And same time tomorrow, which is 9 to 11:30 a.m. Eastern Time, 9 to 11:30 Central, 10 to 12:30 Eastern, and 3 to 5:30, I believe, UTC. Hope I catch you again in the future. Bye-bye.